A developer just released an AI agent framework built on a radical premise. Your AI agent is probably trying to hack you. NanoClaw, released this week, represents a fundamental shift in how we think about AI agent security. While existing frameworks like OpenClaw rely on what developers call implicit trust, essentially hoping the AI behaves, NanoClaw assumes every agent is malicious from the start. The timing couldn't be more relevant. According to Fortune's recent reporting, business leaders still don't trust AI agents for real work. And IT Pro found that IT leaders are missing out on huge financial gains because of these trust issues. Phone Arena's analysis showed consumers aren't ready to trust AI agents on their phones either. The core difference is architectural. OpenClaw runs directly on your host machine by default, with an optional Docker sandbox that most users never enable. NanoClaw flips this completely. Every single agent runs in its own ephemeral container, whether that's Docker on Linux or Apple Container on macOS. Each NanoClaw agent gets 3 layers of isolation. First, a completely separate file system where it can only see explicitly mounted directories. Second, its own Claude session history that can't leak between different contexts. Third, it runs as an unprivileged user with no administrative access. The security model goes deeper than just containers. NanoClaw maintains a mount allow list stored at config/nanoclawlist.json that determines exactly which directories each agent can access. By default, it blocks access to sensitive paths like .sh8, new, .ws, n files, private keys, and credential stores. This addresses a growing concern in AI security: prompt injection attacks. When an AI agent processes external data, say, reading an email or analyzing a document, malicious prompts embedded in that content could theoretically instruct the agent to exfiltrate data or modify files. Traditional application-level security relies on the AI model itself to resist these attacks. NanoClaw's approach is defense in depth. Even if a prompt injection succeeds and the AI tries to escape its sandbox, the operating system's container boundaries act as a hard stop. The agent simply cannot access files or systems outside its designated container, regardless of how cleverly it's been manipulated. The framework also enables context separation that's impossible with traditional approaches. You can run separate agents for personal tasks, work projects, and family coordination, with complete isolation between them. A work agent processing confidential documents can't accidentally leak information to a personal agent, even if both are running simultaneously. Containers are ephemeral, created fresh for each invocation and destroyed afterward. This prevents persistence attacks where a compromised agent might try to leave backdoors or modified files for future exploitation. Every agent session starts from a clean slate. The performance implications are significant. Container creation adds overhead that OpenClaw's direct execution avoids. But the developer argues this trade-off is essential as AI agents become more capable and handle more sensitive tasks. This reflects a broader shift in thinking about AI safety. Early AI systems were primarily research tools or consumer applications with limited system access. As agents become more autonomous and handle enterprise workloads, the security model needs to evolve from trust but verify to never trust, always verify. The enterprise implications are substantial. Companies deploying AI agents for tasks like code review, document analysis, or system administration need assurance that a compromised agent can't access broader infrastructure. NanoClaw provides that assurance through operating system guarantees rather than model promises. For developers, this represents a philosophical choice. Do you optimize for performance and ease of use, accepting the security risks? Or do you prioritize containment, even if it means additional complexity and overhead? The broader AI community is watching this approach closely. As language models become more capable of executing complex tasks and accessing system resources, the attack surface grows exponentially. Container isolation might become the standard approach, not just for experimental frameworks, but for production AI deployments. NanoClaw's release signals that we're moving past the experimental phase of AI agents into production deployment considerations. The question isn't whether AI agents will become widespread, it's whether we'll deploy them securely from the start or retrofit security after incidents occur. The framework is available now on GitHub, and early adoption will likely come from security-conscious enterprises and developers working with sensitive data. Whether this container-first approach becomes the industry standard depends on how the trade-offs between security and performance play out in real-world deployments.